don't need the mic. So our next speaker is Dr. Ramadass. He's the present director of NIOT and is a person who has been trained at IIT Kharagpur, followed by IIT Chennai, where after that I think he has been at NIOT ever since that. Okay, and he's been leading the Deep Ocean mission, which is kind of tasked with exploring the deep ocean and figuring out technological advances by which we can explore the ocean. The stage is yours, Dr. Ramadass.
Good afternoon. I think I have a tremendous disadvantage. I am sandwiched between two stalwarts, Professor Vijay Raghavan, who I consider as my guru, and Dr. Lalitambika, who was heading the manned space mission. Okay, and there are some stock slides actually. Just ignore them, but I will not read everything that is there and all. That is to wake you up from your slumber, because I think the lunch was really sumptuous. So I am from NIOT, National Institute of Ocean Technology. That is an autonomous institution under the Ministry of Earth Sciences. It was started in 2020 and 1993 in IIT Madras in one small room. Now it is actually a 300 crore annual budget institute. And we work on a host of issues like energy and fresh water. We started extracting energy from the waves. But after a detailed study and demonstrations, we found that in our tropical countries, actually here, there is not much energy in the waves actually. But still, standalone system may not have that kind of efficiency. But if you have an array of them, definitely we can have some good amount of power generated. But we perfected one technology called low temperature thermal desalination. We take water, surface sea water. We create vacuum over that one, partial vacuum, and it boils at room temperature, and freshwater vapor rises, leaving the salts behind. If you cool that vapor, you get fresh water. Easier said than done. And what we do is that instead of using conventional refrigeration, we take cold water from the ocean depths, maybe more than 700 meters, 800 meters depth actually, which is at around less than 10 degrees centigrade. Using the heat exchanger, we convert this vapor into water. It's a very safe and very elegant and very cheap actually, economical actually, and less polluting. But the catch is that it is actually meant for islands where the depth is close to the shore. In Chennai and all, we need to have actually go a long way into the sea. So that we have established some 6 plants in Lakshadweep, and we are in the process of establishing some more plants there. And we also try extracting energy from the tides, currents and all. But right now we are into ocean thermal energy conversion, where we exploit the thermal gradient that is available in the oceans. And we also have a strong group working on ocean observation systems. We deploy buoys all along the Indian coast, and we get the data and we give it to the user agencies, including our IMD. And we have also a mandate to deploy tsunami early warning systems in the deep sea, and in the event of any tsunami, at least for the east coast, we'll be able to give 2 hours advanced warning. In association with our Indian National Center for Ocean Information Services, actually in Kois, Hyderabad, we give this, and within 7 minutes, if there is actually earthquake or something like tsunami happens, then within 7 minutes you will be able to get the warning. And we have groups working on coastal and environmental engineering, where we give value-added services. We have restored the beaches in Pondicherry and Kadalur Perikku in Tamil Nadu and all. So that group is working in association with Indian industries. And we have a group working on marine biotechnology. I dare not talk more about that one in front of Professor Vijay Raghavan. He knows more about that than I do. And we have a small fleet of vessels. We have 4 vessels which can go up to from coast to Antarctica, and from shallow water to 6,000 meters water depth. And actually we use them extensively for all our experiments. And of course, to actually this deep, basically you think about DRDO, you know that they send missiles. Of course, ISRO doesn't need any introduction. Department of Atomic Energy is associated with reactors and Pokhran 1 and 2 and all. But if you talk about ocean technology, nobody knows anything about it. It is actually historically it has been so. whereas 200 BC we have records of lunar calendar, but till 1800 AD we didn't have any proper structured ocean exploration. Similarly, this is the Indian Space Odyssey. I think Dr. Tambaka should forgive me if there are some errors in this one, but if you see, I think anyone will answer these first few questions, but last one, who made solo dive to in manned submersible at 11,000 meters water depth? Can anybody answer this question? Yes, who's it? After that, one more is Vasco, one billionaire has done it, but very good actually. James Cameron did it actually solo in Mariana Trench. And okay, Earth is the only planet, known planet with liquid water, and 3/4 of the Earth is covered with water. That means 3/4 of the resources are still unexplored and untapped. Okay, so if you know how to use them properly, they can sustain us for some thousands of years. So far, only 3 people have gone to this maximum depth that is available at the Mariana Trench, so it is less crowded. But inner space is more difficult to conquer. I did not say than the outer space, but okay, inner space is difficult to conquer for the following reasons. One is a dynamic medium, and believe me, I have been traveling in ships actually for hundreds of days, and it may look very romantic, but it's not so actually. When you deploy 25-ton weight with some 30-meter cable at 5,000 meters water depth, and the ship is bouncing up and down, actually it's not really a pleasant experience, but it's really a thrilling one at least. And dynamic medium, and then hydrostatic pressure. Every 10 meters you have 1 bar pressure increase. At 6,000 meters, 600 bar pressure is there. In space, you have to deal with only 1 bar pressure difference. Here, the pressure difference is 600 bar. And density and salinity variations are there. I'll come back to that point. Temperature variations are, corrosion is there. Finally, absorption of electromagnetic radiation. You can control Mars rover sitting from here. But if you drop something at 10 meters water depth, you can't see it, you cannot control it. Electromagnetic waves don't travel long distances except blue-green laser to maybe 100 meters, 200 meters they go. So you have to use sound. Sound is 2 lakh times slower, okay? And the bandwidth is so small, information carrying capacity is so small. So once you are in ocean, unless you have a cable, you are on your own. But you have a cable, reach is limited because there is a huge drag on the cable. So if you have an AUV, autonomous underwater vehicle, it can do on its own, you can program it, but you don't know what it is doing. Okay? So man is more important for the ocean than in the space. And there are many vehicles actually, there is no unique way of categorizing this one, but these are some of the vehicles on which Ministry of Earth Science and Government, National Institute of Ocean Technology is working on. I don't want to go into the details, but the ones we have developed a world-class ROV which can go up to 6,000 meters water depth, do sampling, do survey, and do some kind of intervention. We only made a vehicle. It can be fitted with any sampling mechanism or any tool of your requirement. So it can take biological samples, and we do have a pressure sampler which is imported from outside, and we got actually proposal from IASC to make that indigenously under the Deep Ocean Mission, and we are actively considering that one. So these are the specifications, some of this thing. This is actually the assembled one. This is where we sit and operate this vehicle. And this is the 7,000 meters cable. This is the power. We convert ship power into 460 hertz, 6,000 volts AC. And then we pass through this cable. It's an electro-optical mechanical cable. And we have something similar to satellite launcher and satellite. So they are actually docked together. We drop it into ocean. After reaching designated water depth, there is another winch here. So the thinner cable. So this machine is launched, this robo is launched actually. After working in 400 meter diameter, it is retrieved back and whole thing is lifted back. It's a specialized launching and recovery system for that. And this is our own ship called Sagar Nidhi. This is a picture at the Central Indian Ocean Basin, which is actually 13 degrees south of equator, which is 2,400 kilometers away from Indian coast. So we have used it extensively, including DRDO operations, which I cannot name them here, but for many mineral resources exploration, we have used up to a maximum depth of 5,500 meters. And a variant of this one was developed and we deployed it in Antarctica, and we went under the ice actually, where the continent meets the ocean. And as somebody asked which is the right place for actually conducting all these experiments, International Seabed Authority, United Nations, has allotted one space here. It is actually 5,500 meters water depth at 13 to 15 degrees south and 79 degrees easting, and where the polymetallic nodules, which look like potatoes, are strewn on the seafloor. They are rich in cobalt, nickel, manganese, and iron. Okay, so there are two-dimensional minerals like potatoes. You can harvest them. It is easier said than done because the pressure is very high. You don't have communication. Temperature is very low, and even if you collect it, the seafloor is so soft. You put anything there, actually, the bearing strength is hardly 6 kilopascals. Okay. So if you put anything, it sinks there, and even if you collect these nodules, how do you pump them? If you have a riser, the frictional head is so high, you need around 120 bar positive displacement pump to pump it to the surface with a riser. And then we have started developing this one. We have demonstrated at 500 meters water depth end to end. You may be wondering, 500 meters nodules are not there. We deployed some artificial nodules and mined them. Later, we graduated into 6,000 meters water depth. We have an intermediate station which is just hardly 500 meters above the seafloor, and we collect the nodules, crush them, mix it with seawater. The slurry is pumped to the intermediate station. From here, using a riser, we pump it to the surface. Right now, we are doing it with stages. This is how we size the pump. Actually, we know that actually how to size the mining crawler, that we have done it. We have demonstrated it at 5,270 meters in 2021, and we supply the power from the top, and we take the signals back. We have computers on the controllers on the top and at the bottom. They are actually networked. We have fiber optic converters, and we have fiber optic cables to bring the data to the top and do the commands to the bottom. And we have sized all the things, and we are in the process of proving it in stages. First stage, we want to prove only mining machine. Second stage, the pumping, and third stage, the integration. So I think, as I was telling, we have done, first stage has been completed at 5,270 meters. And coming to manned submersible, as I was telling, there are disadvantages with the different kinds of underwater vehicles. If you combine all the advantages and put a man there, then you have the answer. So application areas are actually, we are making only a platform and a vehicle. You can attach anything to that one, but these are our applications. We have 3 mineral resources to explore. So we are going to use it for them, and for mapping, and even for engineering interventions and shipwrecks, wellheads. You can do anything with that one actually. These are some examples. When actually 2 US American bombers were being refueled, air-to-air refueling was happening. One hydrogen bomb was dropped accidentally to ocean. It was actually discovered using their Alvin submersible, and it was located and it was retrieved. Similarly, the first hydrothermal vent was explored using Shinkai manned submersible of Japan. So it all started in 1932. I am struggling to replicate this experiment. Probably I'll be successful in this June. But in 1932, Charles Bivey actually demonstrated that one up to 1,000 meters water depth. And I think you know him, Professor Calculus, okay? So it's not entirely fictitious character. He was created based on a real life scientist actually, Auguste Piccard. He was a physicist and a balloon explorator actually, and he made the first manned submersible. And later, his son actually perfected it, and it went up to 10,000 meters. What are the important components of manned submersible? First is man. I should correct myself, human. Because many of our women scientists protested when we said manned submersible. So we need humans, okay? Then we need to put them in one enclosure. We don't want to make it like space where only some pilots can go. Here really we want to send ordinary scientists like me at to 6,000 meters water depth. So we want to put them in short sleeve environment where they feel only 1 bar pressure. There is oxygen, 21% oxygen to breathe. CO2 will not cross 500 ppm. So, but you need a shell which can withstand the pressures. So, if you make it with steel, it becomes really very heavy. So, we have to make it with some special grade alloy of titanium, and we need to scrub CO2. I don't know how many of you have seen Apollo 13. It's a serious affair actually. Scrubbing CO2 is a serious problem actually. And we have to supply oxygen. We don't generate oxygen there. And it needs an exostructure, and it needs ballast and trim. We don't want to waste our battery. We use lithium polymer battery. We don't have any resource, ocean thermal energy sources at the bottom. So we use lithium polymer batteries actually. So just using the ballast, we want to really go down and come up, and also adjust our trim. And we need propulsion for going around, and we need batteries, and we need specialized launching and recovery equipment which can launch it at ocean surface. So there are actually a number of manned submersibles that are operational. The latest addition is this by China. Actually, they have done a tremendous really development in this thing, and they have gone up to 10,500 meters water depth in Mariana Trench very recently. And so with all these things, we started making our own manned submersible. It's called MATSYA 6000. The program is called Samudrayan. Okay, this is how it looks like. These are some of the specifications we have mentioned. I am not going into the details of that one, but it actually, these are the dimensions. It weighs 25 tons in air, but in water, it is positively buoyant up to 300 kg. So we have to take water and go down. Okay. So the critical challenges is making the titanium alloy humans actually sphere out of titanium. We are not working in silos. This sphere is being made by VSSC ISRO. Similarly, hydrostatic studies are done by IIT Madras and NSTL Visakhapatnam DRDO. And Indian Navy is helping us in launching and recovering. And we are in close touch with Gaganyaan team for developing, and we have also already developed and perfected and tested the human support facility, actually the life support facility. So these are some of the major subsystems. Okay, so we have grouped into mechanical, electrical, control, navigation, and life support systems. And this is the personal sphere. So it's a challenge. It has to be made in two halves actually. And we selected a titanium actually alloy of grade 23, which has the right strength and which has the minimum that is the density that is required. And this is how it is made. It is made it into two halves like this. It is pressed with 10,000 ton press after getting melted. And these 80 millimeters thick hemispherical object should be welded with electron beam welding, which we don't have that kind of facility. So ISRO is helping us in making in sections, actually in 4 rings instead of 2 hemispheres. And right now, I'm happy to inform you that we have really achieved a lot of progress in this one. Probably by next year, middle, we will be having this 6,000 meter sphere with us. It has to have some windows. So we are making perspex windows, and they are tested for 6,000 meters water depth. And this is how it looks like, and it needs propellers, or actually we call them thrusters. Brushless DC motors are used in this one with Hall effect sensors, and we have 7 of them to move in all 3 directions. And then we have budgeted it actually for doing this work, going down and coming up and doing some work there. If it is stuck there, we have to give it 96 hours support for the human beings. Only hotel loads, of course, but otherwise it has an endurance of 16 hours. So after budgeting, we studied different kind of chemistries actually for the batteries, and we arrived at lithium polymer batteries which can withstand 6,000 meters water depth. So we have procured them, and we are in the process of testing them actually. For actually sending some kind of electrical connectors, fiber optic connectors inside, we cannot have conventional connectors here. So we need something called specialized penetrators. This is how they look like. And control and navigation, of course, we have a triple redundant control and navigation. The pilot should be able to control it. Otherwise, from the top, we should be able to do it by acoustic means. Otherwise, galvanic time releases are there, which actually releases. And this vehicle is made to float. Going down is an effort. Anything fails, it floats. So it is intrinsically safe. And we use conventional inertial navigation system with gyros, fiber optic gyros, of course. We have GPS on the top. We have Doppler velocity log at the bottom. And it has USBL, ultra short baseline, long baseline, which is similar, it is nothing but underwater GPS, acoustic GPS. Of course, we have depth sensor, we have a Kalman filter built into that one, so we get a very good accurate navigation. So this is how it looks like, but everything has to be certified by some agencies like DNV or IRS or somebody. So it is mandatory to have a acoustic telephone. You can't have a duplex perfect communication, but at least you can have a go, no go, like that kind of communication every 15 minutes. So these are some of the components. And this is a communication system. We have underwater voice communication, data modems, and surface communication. So scientific payloads, I have not listed up. Actually, these are the things which we could think of and which we generally use. But any payload, if it has a depth rating, it can be connected to this one. So life support system, how actually 3 human beings have to breathe. They have to inhale oxygen and exhale CO2, and that CO2 to be actually scrubbed. We use lithium hydroxide or sodium hydroxide for actually scrubbing this one. We are actually using the same space technologies for this one. And this is how actually these are the things we provide for the human comfort. But this is how they sit. It is only hardly 2.1 meter diameter, 5 cubic meter space. 3 people have to be cramped actually in that one. They will be sitting like this for almost 12 to 16 hours. And this is the joke I copied from Alvin. So there is no washroom there. Okay, so we have to train ourselves to come up, and it's a serious problem. Actually, we are in touch with our doctors, what kind of food they should take, and whether they can have some kind of hermetically sealed bottles or something, or diapers or something like that. And it's a serious problem. So I am coming to the end of the talk actually. See, you can see, it floats on the surface. We have to open the ballast, water floods in, so it starts going down. It's actually around 300 kg negatively buoyant then. So after going to one place, we keep dropping weights, we achieve neutral buoyancy. We do it with our unmanned vehicles. We have the experience of operating unmanned vehicles at 5,000 meters. And then in the neutrally buoyant conditions, we can move in all directions, we can do all our surveys and all. And for any fine adjustment, we have something called variable buoyancy, which has a positive displacement pump, which has to pump against 600 bar actually. And sometimes it has to take water inside also. It's a challenging technology. So after that, we stop dropping the weights in calibrated way, and we come up. After coming up, we pump the water out so that we get the freeboard, and it is captured by the mothership. So hydrostatic and hydrodynamic studies are being carried out on a 1:3 actually model in IIT Madras and NSTL Visakhapatnam. And this is how it looks like. These are some of the main components. Each component has again subcomponents, and each has to be tested and certified. As a first step towards that one, we made a 500 meter sphere with steel, and we have tested up to 600 meters in the sea. But in our own tank, me and my colleagues sat in this for 4 hours at 7 meters water depth. It doesn't matter whether it is 7 or 7,000 meters, because inside you feel the same pressure. Only thing is whether how much we are getting enough oxygen and we are scrubbing CO2 or not. And it was really satisfactory. So probably in this June, July, we will be going down like in a similar sphere to 500 meters water depth. So this is how we are planning the next activity. The first shallow water operation will happen in February 2024, and then deep water operation will happen in March 2025. So these are some of the submersibles developed by NIOT and our collaborating institutions. And with some pride, I can tell you that India is the only country to have all this kind of submersible under one roof. Other countries, including US, they have some of these things, but not all of them. Okay. And coming to deep ocean mission, Professor Vijayaraghavan has covered it in detail, but it has 6 verticals. I am talking about the first vertical, and we have another vertical actually, that is a third vertical. It is biodiversity, and that's where actually we are using the deep sea sampler and all. And we have advertised for the participation, and we got a lot of proposals, and we are actually shifting to them, and some of them are already sanctioned. And these are some of the areas actually this we have already explored or we want to explore using this submersible. As somebody said, they are so far into the ocean, by the time you reach them, part of the 50% of the team is seasick and rest is homesick actually. So it is. So this is one movie actually, I don't know, it's a 4-minute movie about MATSYA.
Under the Deep Ocean Mission of Ministry of Earth Sciences, Government of India. MATSYA 6000 is an underwater vehicle capable of underwater travel to a depth of 6,000 meters. The underwater travel duration can be for 12-hour duration in normal conditions and 96 hours in abnormal situations. MATSYA 6000 with 10 meters long, 5 meters height and 3 meters wide weighs 28 tons in air. It floats in seawater with a positive buoyancy. MATSYA 6000 design has a 6,000 meter depth rated watertight pressure hull or personnel sphere of 2.1 meter diameter which can accommodate 3 personnel. It has 3 viewports to allow personnel inside to view a subsea environment with the help of illumination provided by underwater lights. With a forward speed of 3 knots in water achievable using underwater thrusters, it can do subsea research, survey sampling and intervention. The ascent and descent motion of the vehicle will be given by the ballast and trim system, which is energy efficient. MATSYA 6000 will be powered by lithium polymer batteries with an energy budget of 100 kilowatt-hours. Redundant control architecture and a fail-safe emergency and salvage systems will be the features of MATSYA 6000 system. An A-frame-based launching and retrieval with support systems in operations research vessel Sagar Nidhi are envisioned for the MATSYA 6000 system. India will be the 6th country to develop a deep-water research submersible along with United States of America, Russia, France, Japan and China. With
Okay, that's the end of my talk actually. So I think I have exceeded my time limit. Okay, so if there are any brief questions, I can listen.
You can definitely do 2 quick questions. Anybody?
And there is anyway frequently asked questions are here. I am going to leave my presentation here. There is nothing secret about it. It is funded by your tax. Okay, so you can read. Pardon?
Where's the application form?
No, actually it's free. All are welcome.
Go ahead.
So, if we want to dive to 5 kilometers, so how much time it will take for diving and just diving and coming?
Yeah, actually it's a good question. Actually, we go with around 20 to 25 meters per minute actually. So it takes around 3 to 4 hours to reach 6 kilometers water depth and 3.5 hours to come back. So you hardly have 5-6 hours time there. But generally these MATSYAs are used at around shallow water, 500 to 2000 meters. So you have more time for the survey. Okay, so it depends on actually the depth.
Okay.
One more quick question.
You said that the idea of harvesting energy from waves fizzled out. What was the reason behind it?
No, I didn't say it fizzled out, but what happened is we started generating around, our plan was to generate 125 kilowatt. Using one oscillating water column actually, we could generate up to 40 kilowatts, but it was very seasonal and it was actually diurnal and so many issues are there. We found and we use the turbines, actually we have to use two-way turbine, okay, whether it's Welsh turbine or you have to have guided vane turbines, we have to see many things actually. But the input is, per meter input is actually less. So even if you have high efficiency in conversion also, very difficult to generate megawatt power. Unless you have an array of those things in the form of a breakwater or something like that, this thing. So I'm not saying it fizzled out, but we developed some kind of buoys and all using this one. So In remote locations, every watt of energy counts. Okay. And somebody asked earlier whether we can have any solar-like thing at the bottom. No, but we can have carbon, magnesium, water, seawater battery, but that also can really give very small power. Okay. Fuel cells definitely we can use. The thing is actually we are proving a concept, we are proving a machine. Later perfecting it and making it more efficient and increasing the endurance and all, that will come. But we are in a hurry to prove the concept actually.